Hello, and welcome to our group's presentation. We are Project CHROMA, which stands for Color Harmonization from Skin Tone Recognition with Optical Monitoring for Adaptive Lighting in Entry-Level Photography.
Our team consists of myself, Matt Scope, Juanita Solania Romero, Juan Trochinsky, and Nikul Patel.
As a reminder, this is our specifications table. As you can see, it is broken up by each subsystem. And our three key dimensionables for the project are in white boxes highlighted with yellow. This is the high-level project design layout. As you can see here, the ICU is placed in front of the person when it is centered onto their face, and we have three light panels surrounding the subject. The following is an overview of the subsystems of the project.
This is our image capture unit. It is our camera module and the brains of our operation. So as you can see here, everything has been 3D modeled and printed for this specific project, even the table mounts, which are able to adjust in height up to 10 centimeters. And each individual component is able to be taken apart and put together. These lens tubes are interchangeable, so they're all the same size mounts, and you're able to change the distance that they can travel along the optical path. It allows for variable working distances, which we are focused on a working distance of 6 to 12 feet. We have three lenses, one plano convex lens that has a 3-inch diameter, a 2-inch plano concave lens for magnification, and a 1-inch achromatic doublet. Now, as you can see here, the outside of the tube rotates, and it allows the lens itself to be pushed forward or back, depending on where the focusing needs to be. And a big part of this was that this was supposed to be modular and is able to be scaled in different ways depending on the user. We have a specific holder for the Raspberry Pi and sensor, as that is stationary. The only thing that moves is the lenses themselves and the actual height that we're working with the table mounts. This is our field of view testing. As you can see here, the ICU is set up, and we are focused on a 20 by 20 square across the way. We are about 11 and a half feet, almost 12 feet away, so at the very edge of our working distance capabilities. And that is the 20 by 20 square that we are focused on. Since a face is on average 20 centimeters long, we want to make sure that we are able to capture a full face in frame. And the center where we are focused on is fully clear.
Our software is designed to process and classify skin tones in real time by leveraging multiple Python scripts and libraries like OpenCV, face recognition, and NumPy. A Raspberry Pi runs the software using a Pi camera module for image capture and MQTT for seamless communication with the lighting system. The dataset we use significantly reduced the time needed to train by providing a diverse set of labeled skin tone images. To ensure accuracy, we standardized image sizes with my resize images script, extracted RGB values from faces with my model training script, and used my facial recognition script to detect and classify live skin tones against the dataset. This system allows for real-time adjustments to the lighting setup based on detected skin tones, optimizing illuminations for diverse subjects. Our real-time facial recognition system successfully detects and classifies skin tones using OpenCV. The facial recognition script processes live camera feeds identifying faces and extracting RGB values from the forehead region for accurate skin tone classification. These values are then compared against the Monk Skin Tones CSV dataset, allowing the system to determine the closest match. Importantly, the test subjects we used in our demo are not included in the training dataset, demonstrating the model's ability to generalize across different individuals. By dynamically assigning skin tones labels, this system enables precise lighting adjustments, improving image quality across diverse complexions. As you can tell from our demo video on the last slide, our trained model performed well, achieving an 83% accuracy rate with only 2 minor misclassification. It consistently classified diverse skin tones, demonstrating strong generalization across different individuals. However, one issue we observed was that after extended use, some subjects began to be misclassified. I currently suspect this is due to insufficient variance in our dataset, which may limit the model's ability to differentiate between closely related skin tones and varying lighting conditions. Moving forward, we'll refine the dataset to include more diverse lighting scenarios and improve overall model robustness.
To properly light our subject, we're utilizing this fill light LED panel system, where our LEDs are being powered by a 24-volt power supply, while a regulator helps step down that voltage to 3.3 volts to power our microcontroller, which is the ESP32. The ESP32 then sends its data through IRLZ44N MOSFET transistors, which help send signals to our PWM LED system, as our system utilizes 5-channel RGB CCT LED lights compared to ARGB LEDs that are typically used with the program that is flashed onto our ESP32 chip, called WLED. Here we have the electrical system of the LED panel. It is connected to the 24-volt 3-amp power supply that plugs into the AC outlet. Into this, and inside we have our main PCB and regulator. The regulator steps down the 24 volts to 3.3 volts for our ESP32, and the ESP32 connects to the Raspberry Pi via Wi-Fi. The reason we have 24 volts is because the LED panel requires 24 volts to be run. We also have the LED panel connected to a fuse just in case it decides to draw more current than it needs. The ESP32 sends its signal via these MOSFETs because we use PWM LEDs compared to ARGB LEDs, which is what WLED normally utilizes. We also have a CP2102 chip that we use to program the ESP32. We have a USB-C port on the side, which allows us to plug it in and program our ESP32. In this case, we flashed it with WLED.
We will now demonstrate the project's progress.
Now, we are able to change the preset operation. So I've changed it to our boot. Then we've got the individual buckets for each of the skin tones. As you can see, the LEDs are changing depending on the preset, generally going warmer for darker skin tones.
Okay, so this is going to be our final demonstration for the CHROMA project. As you can see over here, we have our ICU. On the back, we have our Raspberry Pi. Inside is connected to a Pi camera, and then inside the actual housing of the ICU, we have 3 separate lenses, all pointed at our subject, Juanita. Now, we have displayed on the side so we can see in real time what is classifying Juanita's skin tone. So let's go ahead, start running it. So right now, I read the script and it's currently analyzing Juanita's skin tone and will soon change based on her skin complexion. And this is all being wirelessly transmitted to the PCBs connected to our light boxes. Awesome.
In this test run, we see our subject Kinza is in frame of our ICU. To start, the system resets to daylight at 5100 Kelvin. The system takes 7 samples of her skin tone, then communicates with the LED driver which preset is best for her. We see the system has determined her to be a 6 on the Monk skin tone scale and has changed the preset to bucket 3. This matches with the subject's self-identified 6 on the scale.
Here we have trial 2 with Danielle, who self-identified as a Monk 4 on the skin tone scale, and we can see that the program does in fact identify her as a 4 and change the lights to preset 2. Here is trial 3, and we have our subject Michael, who also identified as a monk 4, and we see that the program is analyzing and getting the correct preset of lights changed appropriately.
This is a table overviewing our analysis of our 10 subjects and their multiple test runs. Now, as you can see here, we have an over 84% accuracy on skin tone analysis and 100% accuracy on the specific preset for each person. We did find, however, that it was much more accurate when the subject, instead of being dead on looking at the camera, if they implemented a more 3/4 profile, that the system was much more reliable and much more accurate.
The CHROMA team thanks you for your time and consideration, and we hope that you enjoyed our presentation.